All right, hashing. It's a word we developers throw around all the time, right? But how many of us really get what's going on under the hood? It's one of those things we think we know, but the details can be pretty tricky. So let's really pull back the curtain and see what's happening.
Okay, let me ask you something. Think about this for a second. You've got a file you just downloaded, then you've got the entire blockchain network, and then there's your Git history. They seem totally unrelated, but they all depend on the exact same core principle to stay secure. What's the one thing, that invisible thread that ties them all together?
Well, the answer is actually super simple. It's hashing. Yep, this one single idea is the cryptographic backbone for so much of the tech we literally use every single day.
So what is it? Put simply, hashing is a process. You take any kind of data, I'm talking a single letter, an entire movie, it doesn't matter, and you feed it into a mathematical function. That function then spits out a fixed-size string of characters. This output, the hash, is like a totally unique digital fingerprint for that original data. And here's the magic part. If you change even one tiny bit of that data, the fingerprint changes completely.
Okay, but here's the thing. You can't just use any old math function. For a hash to be actually useful, especially for security, it has to follow a really strict set of rules. These are the non-negotiables, the things that make a hash function cryptographically strong. And there are 5 big ones we really need to understand. It's got to be deterministic, what we call pre-image resistant, and its close cousin, second pre-image resistant. Then you've got collision resistance, and this really cool thing called the Avalanche Effect. Don't worry, we're going to break down exactly what each of these means.
All right, first up, deterministic. This is super simple, but it's absolutely crucial. All it means is this. If you hash the word hello today, and you come back a year from now and hash hello again with the same algorithm, you are going to get the exact same hash every single time. It's all about consistency.
Next up is pre-image resistance. This is what we mean when we say a hash is a one-way function. Basically, once you have the hash, it's practically impossible to work backward to figure out what the original data was. I love this analogy. It's like trying to unblend a smoothie, right? You know the banana and the strawberries are in there, but good luck trying to pull them back out in their original form. Its close cousin, second pre-image resistance, is just a bit more specific. It says, if I give you an input and its hash, you can't go find another, different input that gives you that same hash.
And that leads us perfectly into collision resistance, which takes things a step further. This property says it should be, and I mean astronomically difficult, to find any 2 different inputs that just happen to produce the exact same hash. This one is so important, and honestly, it's the reason why some older, famous hash algorithms are now considered totally broken.
And finally, we have the Avalanche Effect. And this is where you can really see the power of a good hash function. So take a look at this. We hash hello in all lowercase, and we get this long string of characters. Now watch what happens when we change just one tiny thing. We capitalize the O. And boom! The new hash isn't just a little bit different, it's a completely different, totally unrecognizable string. That tiny change caused an avalanche of changes in the output.
Okay, that's the theory. Cool, right? But where does this stuff actually show up in the real world? Let's talk about where hashing is working behind the scenes every single day.
The short answer is everywhere. You know when you download a big file and you see a checksum? That's a hash, and it's there to make sure your download isn't corrupted. Blockchains? They're basically just chains of blocks linked together by, you guessed it, hashes. That's what makes them so secure. And if you've ever used Git, every single commit you make is identified by a unique hash. It's the fingerprint of your work.
Now, like I mentioned a minute ago, not all hashes are the same. Far from it. As our computers get faster and faster, algorithms that were once the gold standard can eventually get cracked.
This table really tells a story. Take MD5. It's toast. Don't use it for anything security related. Then there's SHA-1, which was huge. Git was built on it, but it was officially broken by Google back in 2017. Today, the workhorse is SHA-2. This is what's securing your web browsing, it's what's behind Bitcoin, and looking to the future, we have SHA-3, which is the next-gen standard designed with a totally different internal structure to hopefully resist future attacks.
Okay, but now we have to talk about the one place where all of this gets kind of turned on its head, passwords. Because for passwords, the very thing you usually want in a hash function, speed, becomes its biggest weakness.
And that leads us to this really critical question. If SHA-256 is so secure that it powers global finance, why is it a terrible choice for storing passwords? What's going on here?
The answer comes down to this one staggering number, 10
Billion. That is roughly how many SHA-256 hashes a decent graphics card can churn through and check per second. An attacker isn't trying to reverse the hash, remember? They're just guessing billions of times a second until they get a match. And suddenly, that incredible speed is working for the bad guys.
So, this is the key takeaway for passwords. The goal is completely different. For something like verifying a file, you want speed. That's what SHA-256 is built for. But for passwords, you want the exact opposite. You want resistance. You need functions like Argon2 or bcrypt that are deliberately slow. They're also what we call memory hard, meaning they gobble up a ton of RAM. All of this just makes it way too expensive and way too slow for an attacker to make those billions of guesses.
But being slow isn't enough. There's one more absolutely essential ingredient, and it's called salting. Here's how it works. Before you hash a user's password, you add a unique, random piece of data to it. That's the salt. Why does this matter? Well, it means that even if two people use the same terrible password, like password123, because they each have a unique salt, their final hashes will be totally different. And this instantly kills a whole class of attacks called rainbow table attacks, which are just giant lists of pre-computed hashes. With unique salts, those lists are useless.
So, putting it all together, the correct, secure way to handle a password looks like this. First, the user gives you their password. Step 2, you generate a brand new random salt just for that user. Then, you combine the password and the salt, and you run that whole thing through a slow, memory-hard function like Argon2. And finally, you store the final hash and the salt together in your database. That's the only way to do it right.
Okay, for our last little section here, let's peek under the hood just a tiny bit. How does a computer actually take your data and create that crazy scrambled fingerprint?
A lot of the classic hash functions, including SHA-2, are built on a clever design called the Merkle-Damgard construction. And the real genius behind it is that it gives you a way to handle data of any size by breaking it down and processing it in nice, neat, fixed-size chunks.
It's basically a loop. First, the algorithm pads your data so it fits perfectly into these blocks. It starts with a fixed initial value, think of it as a blank slate. Then it takes the first block of your data and mixes it with that initial value, which creates a new scrambled value. Then it takes that new value and mixes it with the next block of data, and so on. This repeated mixing is what gives us that awesome avalanche effect we saw earlier. When you finally get to the last block, that final scrambled value, well, that's your hash.
And that really brings us back to one of the most important things to remember about all of this. Hashing is not the same as encryption. It's so easy to mix them up. Encryption is a two-way street. You use a key to lock it, and you use a key to unlock it. You can always get your original data back. Hashing is a one-way street. There is no key. There is no going back.
So there you have it. Hashing is the digital fingerprint of data, an invisible force that's securing everything from your file downloads to the global financial system. So now that you understand this digital fingerprint, it makes you wonder, right? What other invisible technologies that you use every single day are you most curious about?